show. All right. Thank you very much, everyone, for joining us for today's webinar by Ricardo Oliveira, who works in the National Renewable Energy Laboratory in the United States. We appreciate you taking the time to join us. And again, this will be recorded and posted in the Geo4All YouTube channel. So thank you, Ricardo. Please go ahead.
Okay. Hello, everyone. Thank you for taking the time to watch this webinar today. My name is Ricardo Oliveira. I am a geospatial data scientist at the National Renewable Energy Laboratory here in Golden, Colorado, in the US. And today, I'm going to be talking about how we are using FOSS and FOSS4G technologies to solve some of the big data challenges that we face at NREL, more specifically in the field of geospatial science. Before I go to the main messages, I want to talk about some of my personal background and my education. I have a bachelor's in geography and GIS through the University of Colorado, Denver. Right now I'm working on my master's in applied geography and geospatial science. Did some work at the USGS and the private sector, and for the past a little over a year, I've been working as a geospatial data scientist at the National Renewable Energy Laboratory. So all the aspects that I'm going to be talking in this presentation comes from someone who's been working with this at this scale for just over a year. So and I think that's very important, because one of the things I want to echo throughout this presentation is these challenges, they can be solved in very simple ways. And I believe that the main message that I want everyone to take from this webinar is big data is not as scary as it sounds, and you probably don't need any complex system to work with large data sets, especially in a time like now where there's so many buzzwords out there that can kind of create a lot of noise. Well, if I want to work with big data, do I need a very complex system like Hadoop or Spark? Well, actually, no, you don't. You can do a lot using Python and Postgres, and I want to show how. So here are the contents of this presentation. I'll be spending some time with the background on NREL and what we do. Then I'll talk about some of the data sets that we use at the lab, especially in the geospatial science part. Some of the challenges that we face with these data sets, and some of the solutions that we came up to deal with those. And also I want to show some examples of how we are using the technology that I'm going to be talking here today to solve those challenges. So just a quick background for those who are not very familiar with the work we do. NREL, or the National Renewable Energy Laboratory, is one of the many national laboratories under the Department of Energy. We are funded primarily by the government, by the Department of Energy, and basically here I have the official mission statement of the lab. So NREL advances the science and engineering of energy efficiency, sustainable transportation, and renewable power technologies, and provide the knowledge and to integrate and optimize energy systems. NREL is kind of unique in the sense that we are one of the few laboratories that deal with just one very specific aspect of energy. We work with renewable energy, but also from the perspective of sustainable transportation. So we do a lot of research in electrical vehicles and hydrogen and so on. But the geospatial data science, we fit in a very unique position where we have the opportunity to work with almost all groups across the lab. We provide maps, of course, analysis, models, applications, and visualizations that can inform energy planning production. So here on the right-hand side, we have some of the examples of products we created. So we have web applications that show some of our large data sets that was created in partnership with other groups, in this case, the NSRDB data viewer that provides information and also a way for users to download the National Solar Radiation Database. We also have a number of data sets on biomass, hydrogen, wind data, and right at the bottom we have what's called the RE Explorer, which is a series of web applications for international work. We have partners across the globe in an effort to help other governments, other agencies to know more, to learn more about renewable energy and how they can overcome some of the barriers that exist for the integration of these technologies into their own electric grid. So we work all across the board, from web development to data analysis, data management. It's very rich, the fields of knowledge that we have inside our team. So now let's talk about some of the data sets that we work with. Large data sets, as you can imagine, is the part of the day-to-day job at NREL, especially in the geospatial data science group. And most of these large data sets, they are actually spatio-temporal data sets. And what I mean by that is we have data sets that represents radiation across the US. And we have not just the location of these data points, but also have how the values for each data point changes across the year at, let's say, an hourly time step or even a semi-hourly time step. So that's what I mean by spatio-temporal data set. And those are what's called the resource data sets. So in the example that I just gave you, there will be a solar resource data set. So if you want to model a system, a utility photovoltaic system, we need to know at a given location how much solar radiation that location is getting throughout the year. And the seasonality is very important. The spatial resolution is very important. And another example would be the wind toolkit, which is, for, as the name says, for wind. So we have the average wind speed for that given hour. We have the direction, we have air pressure. So all those data points, they are key for us to be able to model energy systems at a geographic perspective. So now I want to talk about a little more in depth about those data sets. So first, I have the wind toolkit here. So the wind toolkit is a data set that's 2 kilometer spatial resolution, which equates to more or less 2.5 million points just for the continental US. And the map on the left was created by our in-house cartographer. Shows the wind speed at a 100-meter hub height. And that's just a side note, that data set we have at 3 different hub heights, because wind turbines can be installed at those heights. So we have 100 meters, 80 meters, and 120 meters, I believe. We have 7 years worth of data, and that is our hourly data set. So it's around 8,700 time steps for a year. And at the end, we have each data set for each year is about 569 gigs. So just look at that, you can see that's a considerable data set to work with. And later this year, or probably next year, we're gonna have another data set also for the wind toolkit, but instead of hourly data, we're gonna have a 5-minute time steps. And that means that each year will be about 25 terabytes of data. So the chance that we have now will only increase as the data increases, because one thing that's very important to be able to model systems in a very faithful way is the time resolution. For some data sets, time resolution is even more important than spatial resolution. For instance, PV, solar photovoltaics, the spatial autocorrelation doesn't have such an impact as it has for wind, because terrain is not very impactful for the radiation, but the time resolution is very important. So it gets to a point where to have a data set with a finer spatial resolution is not as, doesn't yield the same improvements than having a finer temporal resolution. So that's why we are working with other groups in the lab to create this 5-minute data set for the Wind toolkit. So it is very exciting, and I think that the analysis that this finer temporal resolution will provide will be fantastic. The next one is the National Solar Radiation Database, or NSRDB for short. So that, as I said, the spatial correlation is not as impactful, so it is a 4-kilometer spatial resolution. It is 2 million points for the continental US, but for this one we have 17 years worth of data, mainly because this data set is created from other satellite data sets, primarily I believe MERA from NASA. So we are able to create a larger year span for this data set. This one is half hour, but it has more attributes. And the next slide I will explain what I mean by that. So each NSRDB, each year of the NSRDB is 1.6 terabytes. So again, it's a considerable data set again. But here are the challenges with those data sets, mainly because of the size of those. And again, NSRDB 1.6 terabytes, Wind toolkit will be 25 terabytes in the future. And as you can imagine, data don't fit in memory. Even with the supercomputer that we have called Peregrine in the lab, we can only fit 200 gigs of data in memory at once. And it's clearly not enough to even have half of the Wind toolkit there. Another point is we need to be able to conduct really complex analysis for each data point. So if you want to know how much generation each data point from the NSRDB or the Wind toolkit can produce in an optimal system, we have to be able to do this for 2 million points. And this analysis by itself is already very complex. So imagine multiplying that by 2 million, and more importantly, perhaps, is we need answers in hours, not weeks. So the way we solve these challenges is actually very simple. The first one, well, if we can't feed the entire data set in memory, we just read part of the data set. So we read the file in chunks. The next slide I'll explain why and how we do that. The next one, we basically, that's a bit more philosophical from a coding perspective, I believe. If we need to conduct really complex analysis on each data point, one thing we do is we try to break our analysis into logical modules, and we run each module separate. So, for instance, if I want to know how much generation, how much it would cost to generate electricity from a wind turbine at a given point, before that, I need to know how much energy that point can generate. So the way we do it, we first calculate generation, and then we would calculate the cost, and then whatever comes after that. So by breaking your whole analysis into logical modules, we can optimize the runtime for the whole analysis. And again, if we need answers in hours, not weeks, that means that we have to process each data point at the same time. Maybe we need to process a couple hundreds of points at the same time, or a couple thousands, and we do that in parallel. So as I mentioned, unfortunately I don't have a slide here, but at NREL we have a supercomputer called Peregrine, and with this supercomputer, one thing we can do, we can basically check out a bunch of nodes, a bunch of cores at the same time, and have, let's say, 120 cores to use for single analysis. So, and that's what allows us to basically process 2 million points in a couple hours or even 30 minutes. It's because we take our load and we basically split that across multiple cores on that computer. And I have a slide here that explains a bit more in depth how we do that through Python. So now I want to talk about some of the tools we use. Probably the most important tool is actually a data format. It's called the HDF5, which was created and is supported by the HDF group, research group. Sorry. So HDF5 is a data model, a library, and a data format. It supports extremely efficient I/O and allows for a really complex schema setting internally. And right here on the left-hand side, I have an example what I mean by schema. When you install the HDF on your computer, the whole library and the utilities, you have a number of command line utilities that you can use to interact with an HDF file. So the name here is the NSRDB for the year 2015, as you can see, 1.6 terabytes. And the extension is just .h5. So inside that file, what we have, in fact, is a number of different data sets. And each data set you can see as being a table, okay? So we have the meta, and that's where we store things like the latitude and longitude of a data point, so 2 million points here. And each data set, we have row-wise, we have time steps. So 17,000 here is each half-hour bin across the year. And by row and by column, we have the location. So in a single file, we can have things like DHI, DNI, which informs radiation. We have surface temperature, pressure, wind direction, wind speed at the surface. We have a number of data that we can use, but I think the key here is everything lives in a single file. So for data management purposes, this is great because we don't have to worry about, oh, I have to move the 2015 year between folders. I don't have to worry if I'm leaving some data set behind. No, everything is coming in a single file, which is really great. So taking the Python route, there are a number of data sets, there are a number of libraries that can read HDF files. So the most important perhaps is the H5Py library, and you can even use pandas if you have H5Py. And for those who have some experience with Python, actually in the next slide I'll talk more about Python, so I'll do that. So yes, with Python we have libraries that can read HDF5 file, and more importantly, you don't need to read the whole file if you want to manipulate the data. It is possible to, instead of opening the entire file, you open the file, but you only read a small chunk of it. So instead of reading 1.6 terabytes, I can say, okay, from the 2015 year, I'm gonna read the DHI and DNI data sets, but I'm gonna read just 10 points. And that's less than a Mac. That's less than 1 megabyte in memory that you are holding in order to process and things like that. So, and that's something that HDF allows you to do. And that's why I said that HDF is probably the most important piece of technology we use. And of course, it is completely free and open source. It has a huge community behind. A number of people use HDF in scientific settings, academia, and even industry. So it's always great to use a format that is an industry standard, and HDF is definitely one of those. And once you read the data, in Python, you manipulate the same way you manipulate as any other NumPy array. And next slide I'll talk about what I mean by NumPy array, for those who are not familiar. So that means that you have a plethora of of functions to use with your data, and which creating increases the possibilities of the things you can use, we can do with the data. And Python is probably one of the other main pillar of what we do. Across the lab, people use a number of different languages, from Haskell to C, Java, yeah. But Python is probably one of the most popular. Everyone in the geospatial data science team knows Python and knows Python well. So, and we are constantly sharing knowledge about how to do things right in Python. So it has been a great learning experience, especially for me. But and I believe that the reason for why we use Python is first because it's a very elegant and efficient language. We call Python as having batteries included. That means that you install Python on your computer, and you already have a number of libraries to do, from mathematical operations to just parsing text or scraping web pages. You can do a lot with what Python gives you. But Python also has this really rich ecosystem of libraries out there. And here are just a number of lists of just a few of the libraries that we use and why we use. And from my perspective, maybe some other team member will have a different idea, different perspective on this. But these are probably the most important for us. So the first one is the H5Py. As I said, that's what allows us to read an HF file into a Python script and process that there. The second one is NumPy. NumPy is for numerical manipulations, and you can see NumPy as doing matrices operations in Python. So if you read a data set from an HDF, what you actually have is an array. So you have, in columns, we have the location, each data point, and rows, you have timestamps. So that's essentially an array that you can process using NumPy. But you can also use another library called Pandas. Pandas, they call it being a general purpose sort of data analysis library. You can imagine as a data frame. Pandas has this idea of a data frame, which is essentially a table. So you can do a number of table-like operations inside Python. And directly related to Pandas, we have GeoPandas, which adds a number of GIS capabilities to those data frames. So now one column can actually be a geometry, and with the geometry you can do buffers, you can do intersects, you can do clipping, you can do a lot. And GeoPandas is great, it's very efficient as well. So for visualization, we have Seaborn. And just a side note, the visualization ecosystem inside Python is huge, and it's growing like crazy. There are probably hundreds of libraries out there to produce charts, to do interactive chart graphs, but I personally like Seaborn because the Seaborn syntax is very simple. It correlates really well with matplotlib, which is the basic chart library in Python. And also, Seaborn also gives you some statistical functions. So basically, it has right off the box allows you to do box plots, for instance. And on those box plots, you have mean, you have outliers, have all your whiskers. It's great. It's a great library, and it looks really good right off the box. And that's, for me, it's really key because sometimes you want a chart, but you don't want to spend a lot of time making that extremely pretty. So a library like Seaborn just gives you a chart that's really beautiful, actually. And lastly, we have Scoop. Scoop is what allows us to run Python in multiple cores on the supercomputer. So as I said, Python is what's called a batteries included language. and that's because of the number of libraries that it gives you right off the box. And one of those libraries is called multiprocessing. So if you install Python and if you use multiprocessing, go through the documentation and all that, you can, in the same day, run a Python script across all cores in your local computer. And our computers today, we have between 4, 8 cores, and some even have 12 cores. And Python allows you to take advantage of all those cores that otherwise would just sit idly doing nothing as you process your data. But what multiprocessing don't allow you to do is to take your script and distribute that across multiple nodes, which is how a supercomputer works, right? So we go to a supercomputer and say, oh, today I want to use 4 nodes, and each node has 24 cores. So suddenly you have at your disposal, more than 100 cores to use, but they all sit in separate nodes. What Scoop does behind the scenes, and it's very efficient the way it does, it takes care of all that communication between nodes. It takes care of all of that. So you don't need to worry about, setting up sort of kind of manually the way each core, each node gonna take the job and gonna process, you're gonna send it back to a central node to put it together. No, Scoop does all that heavy lifting for you. And I personally think Scoop is simpler to set up than multiprocessing. So even if I'm running something on my 4 cores on my local laptop, I use Scoop because I think it's more elegant the way you have to write your code and things like that. So it's great if you're looking to go into parallelization in Python. I highly suggest that you take a look at Scoop and see if that would fills your needs. And as you can imagine, all these libraries, they're all on GitHub. They have a pretty decent size community behind. So if you have problems, or if you want to learn, there are a number of libraries, there are a lot of people there who really kind of willing to help. And again, I believe we all know that's one of the keys of why we use open source software in our work, is mainly because of the community a lot of times. And the last tool I want to talk about is Postgres and PostGIS. So I believe that Postgres, even for those who are not database savvy or don't use database on their day-to-day, they probably already heard about Postgres some point, and that's probably because Postgres is the most powerful relational database during operation. Postgres is behind really mission critic operations in all sorts of environments, from GIS to banking to data centers. Postgres is all over the place, and that's because Postgres has been around for a long time, and it's under constant development, and with each new version of Postgres, you have all these jumps in performance, and suddenly your queries are operating in parallel. So they become twice as faster as 2 versions behind. It's great. And with Postgres, we can install a spatial extension called PostGIS, which basically enables us to, 1, have geometries on our tables, and 2, allows us to perform spatial operations within the database system. So here on the right-hand side, I have 2 small snippets of SQL code. The first one here is just creating a table, and as you can see, one of the columns of this table is actually a geography column. It holds geometries, it holds distances, it has a projection. So now the opportunities are just endless, right? And they are indeed, because PostGIS supports both vectors and rasters. So here I have a small query that all it's doing is it's taking a bunch of vectors for these 4 countries, and it's using those to flip a raster. So you see how easy and straightforward an operation like this is inside the database. mainly because of PostgIS, because PostgIS gives you like this function, st-intersects. So now you can intersect raster and raster, vector and vector, vector and raster. You can do a lot with those. And of course, you can manipulate Postgres. You can manipulate queries inside Postgres using Python. And you can get data from Postgres into a Python script using libraries like SQL Alchemy and CyclePG. There are other libraries, I believe, but those are for sure the two main ones. So if you want to get into this hybrid of Python and Postgres databases, these are the libraries that I would suggest you to check out first. What I have now here is 3 examples of how we take all these technologies and how we put it together to actually solve our problems. So here I have HDF and Python example. So basically we have your data, your 1.6 terabytes or 25 terabytes data sitting inside an HDF, okay? And you want to, let's say, you want to take a year and you want to calculate the mean of that year for, let's suppose, wind speed or wind direction. So what you do is very simple. Instead of reading all locations at the same time, you read HDF, but you take the number of locations you have and you split it into chunks of hundreds, let's say, example. And then using scoop, you can pass each chunk of 100 to a worker. And here a worker basically means a core, a processing core. And then you say to that processing core, okay, take this 100 chunks that has hourly or half-hourly data and give me the mean for that year, for that point, for each of those hundreds. So you pass a bunch of data, and then you get 100 values back for each mean. And you keep doing that. You keep doing that until you are done with your 2 million points. And once you're done, you just take those values and combine into a single array, for instance. And then you just write it back to a new HDF or a CSV or a database or whatever. But you see how the key here is that you're taking your analysis logic and you're splitting that into multiple workers or cores, and you're letting each core work in a small fraction of your data. And that's how we take something that would take like a week to process in a single core, we can do it in like 10 minutes, because you have hundreds of cores working on the same logic at the same time, but for different data. And so that's very generic display here, but that's the key logic behind it. And the same can be done, but instead of HDF, with a Postgres database. Let's say you have 2.5 million buildings, a table of 2.5 million buildings, okay? So 2.5 million points. And you want to intersect each building against census blocks. So basically, your question is how many buildings each census blocks have across the US. And as you can imagine, there are dozens of thousands. To be very honest, I don't know what the correct number is. But with Postgres alone, you can write a query and you can let it run that. Okay, give me that count. But there's a really good chance that the amount of data that you are intersecting at the same time, even if you have all the indexes properly created and all that, it's gonna take a while. So what I found is that instead of saying to the database, intersect this 2.5 million points, I say intersect this 50 points against the blocks. The operation time, the computational time is much lower because it's a cheaper operation. So what I'm doing is I'm using Python to read the size of the table I want to process. So in this case, I just ask Python to send a query to the database and say, okay, how many rows do you have? I have 2.5 million rows. I take those 2.5 million, I split into chunks, octets, or hundreds or whatever, and then again using scoop, I pass the chunk, I pass the number. So each worker from scoop actually gonna fire a new query to the database. So instead of saying intersect 2.5 million points, the query will say intersect these 50 points here for me. So I have like 30 cores, I have 100 cores, it really doesn't matter, because the way Postgres works is you can have, depending on the size of your server, of course, you can have hundreds of queries running at the same time, and they will not affect the performance of each other. Of course, you have to be a bit careful depending on the spatial operation you have to do. So spatial operations are much more expensive memory-wise, so you always end up having the risk of kind of running out of memory on your server if you're running thousands of spatial queries at the same time. But I would say that you can easily run like 50, 100 queries at the same time, and it'll be fine. So each worker sends the query, Postgres does all the crunch, does whatever it has to do, and sends the results back and to Python. And Python takes those results, combine into a single table, and then I can write that to CSV, to an HDF, to a database. Doesn't matter. You can do whatever you want. But you see how how this combination of Python and Postgres can allow for some really interesting analysis, because then you don't need to have your data extracted from Postgres into some other file format before you ingest that using Python. No, you can just do everything in a single operation. You read from the database into the Python script, and you manipulate, you send queries to the database, get results back, combine. You can do a lot. So the last thing I want to talk about is how we distributed some of those large data sets to the public. The way it works, again, and everything is possible because of the way the HDF works. We have an API, and that's specifically for the NSRDB viewer. The user goes to the NSRDB viewer, he grabs a point or a region, and it sends a request. Okay, please give me data for this region or for this point for this year, and I want this data, I want DNI, I want DHI, I want temperature, doesn't matter. So that request goes to an API that's written in Ruby and actually runs JRuby as well, which is sort of a wrapper around Java code. And the API goes to the HDF that sits on the supercomputer, grabs only the chunks it needs to grab, prepares, creates whatever data format the user needs, and then sends that back to the user in the form of a link to download the data. So if it wasn't for HDF, I'm really not sure how an operation like this would be possible, because HDF is, again, what's allowing us to only read a small part of the file instead of reading the whole thing at once. And again, that's how we make that data available to the public. So basically, you guys have 1.6 terabytes worth of data for each year at your fingertips, and you can download quite easily through the NSRDB viewer. I highly suggest you guys check that link. Okay, so here's the conclusion. And as I said in the beginning, big data is not as scary as it sounds. You just need to deconstruct some of the challenges that it brings. Of course, it don't fit in memory, so don't try to fit in memory. See if you can read just a small chunk of the file and work with that, and try to create a logic that can do whatever you need to do, but on each small chunk at a time. You don't need a complex system to work with large data sets. It is very true. You may have a complex system, you may have Hadoop, you may have Spark, you may have something like Cassandra, but it requires some very specific knowledge to support those systems. And the geospatial data science team, we are not computer scientists, we are geographers. We're looking at how geography and GIS can help solve some of the big renewable energy challenges we have. Okay, so we really don't have either time or knowledge to set up these complex systems. But we do know Python, and we do Python well. So can we solve those challenges with Python and Postgres? Yes, absolutely, you can. And it may take a while for you to wrap your head around some of the concepts and kind of the challenges related to memory and I/O and all those things. But it's all Python. And I'll just reinforce that what I just said. You can go really far using Python and Postgres. So for those who are starting on the GIS world and you decide that yes, GIS is what I want to do, I want to expand my knowledge in geospatial science, I would say learn Python and learn Postgres. Those are probably the most important tools you ever have on your toolbox. Even if you decide that, Python, Postgres, over the place, from data science to finance. You can do a lot with those technologies. So that's my presentation, and once again, thank you very much for taking your time to watch this webinar. Here's my email. Feel free to send any questions to me or any ideas. Always like to talk to people. So yeah, thank you.
Excellent. Thank you very much, Ricardo. That was an excellent presentation.